We are very happy to have Jiang, who will tell us about the spin Calogero-Moser systems and their superintegrability. So,
okay, thanks for the introduction, and I would first thank the organizers, and I'm honored to have a chance to introduce our work. This work is based on the joint work with Chen Zhuo, Nikolai Rostikin, and Xiao Husman. Okay, this is about 3 years work, so it's okay. Let's begin. This is the part of the talk. The first, I will introduce get a quick recall of the Calogero-Moser systems and also the spin Calogero-Moser systems, and then talk about the superintegrability and the definition, different kinds of definitions, and the last part is a concrete example, a tall example of SU3. It's the easiest one of to show our results. Okay. So first of all, the Calogero-Moser system. I think most of for the mathematicians in dynamical systems, they are quite familiar with this. It describes n particles living in the one-dimensional space. For one-dimensional space, it can be a line or a circle, a closed circle. And here it is the Hamiltonian, like this. It works like this, in which the P's are momenta, and Gi here, sorry. Okay, here the Q, here are the positions, and the G here are the coupling constants. So for physics, they are quite, this is important, but in mathematics, we usually set this G to be 1 and M to be 1, the mass. Okay, and the important part is the potential. This V is the potential. Potential function here, we require that it has a second order pull at the origin. It means usually it is 1 over something square, like this. So it depends on this potential function. So if the potential function is chosen different potential function, they have different behavior. So the classical or the usual one cases are the following. The simplest one is the rational case. Here, the potential function v, it looks like 1 over x squared, like this. It is the rational one. And we also have the hyperbolic case. Here, it is hyperbolic sinus, like this. It is also like also a second pull here at the pull of second order. And the trigonometric case, we also call it a Calogero-Sutherland system. Now it is the sinus. So here, for the third one, it describes the particles living on the circle because it can be periodic. As the sinus here, it is a periodic function. So it can be just like a circle. It can be has a periodic phenomenon. And the last one is more complicated. It is called elliptic case. It's related to the very structural function and is related to the algebraic geometry. And here I'm not quite familiar with the last part, so we will focus on the first three parts. So next, for the Calogero-Moser system, it is almost the simplest one to be the integrable system. For the rational case, it is proved in 1975 by Moser that CM system is Liouville integrable using Lax pair method. For the Liouville integrability, it is quite well known. It means that on two-dimensional space, a symplectic manifold, there are a half number of first integrals of motions. They are independent and they commute pairwise. So this is quite classical. This is for the rational case. And also for the hyperbolic and trigonometric case, this integrability also are also were established in the similar argument. And for the elliptic case, the most complicated case, in 1980s, we use some, for example, use the spectral curve, spectral curve to obtain the integral of motions. So for the classic Calogero-Moser system, we always have the Liouville integrability. It means that we have enough integrals of motions. Okay, this is the classic one. And the Calogero-Moser system can be obtained from Hamiltonian reduction. Before that, it is always, you can see that here, it can be described as just as the use to study the Hamiltonian functions. And here, we use, in the 1980s, we have the method of Hamiltonian reduction. In fact, it is realized like this. Let G be a simple Lie group, and G is Lie algebra. And we consider the action G on the cotangent space, cotangent bundle T star G. And with trivialization, we can left or right. It is equivalent to the dual of G cross the big G, the group. And the action is given is diagonal. It means that each vector, each component, it is a conjugation, like this. This part, this is the action. This is the action. This action is Hamiltonian, so we can have this moment map J, and this J is quite standard. It's quite clear. By this makes this X in the dual and the gamma in the group G, and it sends this X gamma, this pair, to the X minus gamma inverse. It's a coadjoint orbit. Yes, coadjoint representation here. X minus the adjoint coadjoint representation. So now we pick an element G, Xi in the dual, and let OXi be the coadjoint orbit in G in the dual. So the reduced space, also the phase space, refer to the quotient. This is the classic Hamiltonian reduction. This Xi is a simplex leaf of this J inverse the orbit. This is the Poisson, and after the quotient, we get a symplectic. Usually, it is a symplectic manifold or symplectic space. This is a quite classic Hamiltonian reduction, and now we consider the function, the trace function. It's also classic. The trace function is the trace x squared, and then it is as it is invariant under the diagonal coadjoint action by G. So the momentum map J is also G equivalent. So this trace function can be regarded as a function on the reduced space, so denoted by H2. So in particular, if G is chosen as the special unitary matrices group, SUN or SLN, like this, and C is chosen like this particular form. It means C, 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 and minus n minus 1C. We call it rank 1, because this rank 1, it means that C minus a scalar matrix, it is of rank 1. This matrix is rank 1. This C minus a scalar matrix, the rank of this new matrix is 1. So then it's true. It's just the Hamiltonian function we defined before. In the previous page, it is. So that means that in the classic way and from the Hamiltonian reduction, they are all the Calogero-Moser system, and we know that the Calogero-Moser system is integrable, Liouville integrable. We need to find n first integral of motions. In fact, from the Hamiltonian reduction viewpoint, it is quite easy because the trace function is always the invariance. So here the trace with the trace square here and the trace cubic and of power 3, 4, 5 to n, it can get n minus 1 independent integrals of motion. Yeah. So we can directly check that the computer, yeah, this is a classic result. So now, up to now, we discussed about the rank 1 case. This is if we choose a particular G and a particular C, then we get the Calogero-Moser system. So natural question is, what if C is not like this? Because of this co-adjoint orbit OPC is quite special. There are many other generic, for example, generic co-adjoint orbits. For example, the C is if the C is regular, it means all the eigenvalues, the C eigenvalues are distinct. So we can that kind of co-adjoint more often, more common. So we can want to study about the other C or co-adjoint orbit. So we should introduce the spin Calogero-Moser system. So there are also two ways to achieve this spin Calogero-Moser system. One way is as before. We just see that we introduce the spin variables. For example, mu ij, mu gi here, mu, and here, and for the classical one, here it is 1. This is constant. But here we have spin variables. We just add this one, and add the space is bigger, phase space is bigger, and we have more variables. And the P and Q are still the momentum and the positions respectively. From the Hamiltonian reduction viewpoint, we can see that equivalently, if this C is of rank bigger than 1, rank it means not the rank of this matrix, but the rank it means that this C minus a scalar or plus a scalar matrix. That matrix, the rank of that matrix. We still have these functions, trace functions, because the trace functions is still there, and it is still G equivariant. So the trace function, we still have n minus 1 integrals of motion, and they commute pairwise. So there's no problem. So can we expect there's a natural question can we still expect the Liouville integrability? The answer here, this question is easy. The answer is no. And because the dimension of the phase grows, we have more variables, the spin variables, but there are not enough integrals of motion at present. So how can we describe this spin Calogero-Moser system? So we should have the superintegrability, this notion. So what is superintegrability? There are several definitions of this. In fact, the superintegrability, it is defined in 1972 and 1978. And it's a long history. And at the beginning, it is from the dynamical systems. They just define just like this. I say that there are two pairs there are still some smooth functions. But these functions, they are two groups. They are separated into two groups. The first group that we have this Hamiltonian H1, and we still have some other smooth functions, and H2 and H2n minus k. K is smaller than n. For this n minus k functions, we have two groups. We divided into two groups. The first group is the center. It means the first k. The first k, they commute pairwise. It means H1 to Hk, they commute pairwise. And from the k plus 1 to n minus k here, we have that they commute with the center. it means the first key functions and the last 2n minus 2 key functions, they commute. But the last 2n minus 2 key functions, we do not guarantee that they commute under the Poisson bracket. So there are two parts of them. See that, yes. Here, and of course, we demand that all these functions are functionally independent. The rank of these functions is 2n minus k. Yes, so we can see that we still have the first the integrals of motions. We have 2n minus k integrals of motions, but they do not commute pairwise. Only part of them, the first key of them, they commute pairwise. This is the difference between the superintegrability and the Liouville integrability. So a particular case is that k equals to n. When k equals to n, so it means that there's all first integral, all integrals of motions they commute pairwise. So it is become the classic Liouville integrability. Okay, first I will show maybe from this definition we have some other equivalent definition. From the algebraic viewpoint, we can describe this superintegrability in one phrase. It's like this: a superintegrable symplectic manifold of dimension 2n consists of the Poisson bracket as a Poisson subalgebra. Subalgebra, it is in the algebra of smooth functions on M to n. This subalgebra A is of 2n minus k, and also this A has a Poisson center ZA, and this A is of rank k. So in the algebraic way, the description is much easier. There are two parts. The point part is this algebra A, and the other part, the third part is its center, just like this. So the rank is classic. It means the rank is a equivalent to say that there are 2n minus k generators. They are functionally independent. Yes. So okay. So this is, we can also have a geometric realization. It means that we can also look at this superintegrability from geometric viewpoint. An equivalent definition is like this. We can consider that as we know that if you are familiar with the spect, you can consider that this part, this M, we first see that this M just the spect of the algebra of smooth functions on M. And this is the spect of A, the middle part, and this B is just the spect of the center of A. So in the geometric part, we can see that this M is still a symplectic manifold of M of dimensional 2n. And this system, there is a Poisson manifold in the middle, and of dimension 2n minus k. And there's also Poisson manifold with the trivial Poisson bracket structure of dimension k. And here, the important part is there exists the psi and the pi. They are Poisson surjection. It means this is Poisson map first. Poisson map. And it is also surjective. It means it is onto. So with this, we can see that the component, if we select a generic point in BK, there is a fiber here. It's connected components of this fiber, pi inverse B, here in P. It is a symplectic leaf in this Poisson map. And this psi, it is a co-isotropic map, co-isotropic. You can consider it like this. Yes, so this is a geometric realization. We can just, this these three, in fact, these three definitions are almost equivalent. You can now see it because there's for the geometric realization, it's not the there are some generically they are the same, but there are some singular points. They arises some bad behavior, but in general they are the same. So for the superintegrability, we still have some good properties. For example, the classic Arnold-Liouville theorem still holds. The classic code is that in a neighborhood of I think this is quite similar to the classic Arnold-Liouville theorem. It says that in the neighborhood, tubular neighborhood of the regular fiber, we can always have the action angle coordinates and write this tubular neighborhood as something like this, as a torus of dimension k and a disk of dimension k. So and another symplectic manifold U. And here we have the action coordinate h. This is the Hamiltonian functions. And this is the angle coordinates theta. And so this is, in fact, this is the torus, just like the torus, the coordinates on the torus. And this omega tilde, here it is the remaining part on this symplectic manifold. Yeah, so we have this decomposition in local decomposition. And of course, we hope to have a global one, but it's very difficult to find a global one. So if we want to have if having the superintegrability, the next work is to find its action angle coordinates. To have this, if we can have the action angle coordinates, it means that we understand the system quite clearly, and we can express this system explicitly. So the final goal is to find the action angle coordinates. Okay, now we can see that again. We should like to see that result by Rustikin in 2003. It says that spin Calogero-Moser systems are superintegrable generically. Here, the generically means okay, I will explain why we will say that generically. Why take the generic point. The idea is we use the third definition, and the method is to construct the sequence. To construct a symplectic manifold M. Yeah, just like before, it is already there by Hamiltonian reduction in the phase space. And in the middle, how to construct a Poisson manifold. And the B, it is easier because it is just the action and the action coordinates, just the coordinates, the functions of the B. So it is the center. We know it. So how to describe this P, the Poisson structure, and have this pi and psi and pi. So the M, it is said that it is isomorphic to this part, W via group, and H the Gardner group, and the regular part, the cotangent bundle. And this O prime is another quotient space by Hamiltonian reduction of this Gardner, acting diagonally on this orbit, on a co-adjoint orbit in the dual of Lie algebra. So this is the phase space. This is the phase space. So, and we should know that this the second part is to prove is that M is isomorphic to an open dense regular part. This one is our. We said that this is the we see that as similar to the classical Calogero-Moser system. This is this is the reduced space. This is the phase space, and Rustikin proved that this one and this one are isomorphic. So And then we just define some psi, just like this one. Okay, this is the momentum. This is just the projection of the Poisson bracket is from this G star over G star, G star times G star, and this pi is just the classical projection. So to the first component. So with this in fact this construction is natural, but the work is to show that the dimension of this one, the dimension of the P and the dimension of the K. This one, it means that the fiber of psi, the fiber of psi over a generic point in P is just the dimension of B. Yeah, I repeat it maybe here. That means that the dimension of the fiber of psi over P at a generic point is just the dimension of B. So if we can prove this one, it means that the dimension of P plus the dimension of B is the dimension of M. Okay. Okay, this is the result. And this is one problem for our reduction. We should say that I would like to remark that here in his paper in 2003, all the quotient here are GIT quotient. So as we know that the GIT quotient is nicer than the normal ordinary quotient. The ordinary quotient it may even be non-Hausdorff. So here the space is very good. But if we consider the real orbit space, we have the quotient space in the ordinary quotient maybe no longer a smooth manifold, but it might be a stratified space when this action is not free, is not locally free. So if we consider not directly this one, if we consider not the space not isomorphic to this one, but directly the quotient, the ordinary quotient like this, then the phase space is a stratified symplectic space. So we should there's some so the stratified space is quite complicated. There's a very it is studied by many people, and there's some concrete. There are some pictures definition. But here I would like to say that a stratified space. What is it? It is a topological space. You can think of it as a disjoint union of manifolds of different dimensions, with some frontier condition and Whitney condition. You can if this you can refer some book read this definition, but you can consider it as a manifold with boundary, or some manifold with a corner. And for example, the simplest one is a cone. A cone, you can think of the vertex as a point. The point vertex is a lower dimensional, for zero-dimensional space, and the other part are the two-dimensional space. So with a corner, this different, you can say that it's a topological space. It's good, but the differential C infinity structure is quite complicated. So and you can consider a cubic with corners. You can consider the cubic the inner part are the three-dimensional, and the surface are two-dimensional, and they are the one-dimensional, two-dimensional thing like. And I draw a picture here, just like a paper plane here, on the blackboard. You can see that this one, you have a paper plane. You can use. This is also a stratified space. There are several parts. The colored part are the two-dimensional surface, and in the intersection they are the one-dimensional manifold, and the vertices there are 1, 2, 3, 4, 5 vertices. 1, 2, 3, 4, 5. 5 vertices. They are the 0-dimensional points. So this kind of thing is a stratified space. So it has some frontier condition is the key for the stratified space. So we should consider we simply roughly speaking, it is a disjoint union of manifolds of different dimensions. We can think of it like this. Okay. And an important theorem of Schwann and Riemann in 1990 tells us that the quotient space, this one, SC, is a stratified symplectic space. It means that for each stratum it equipped with a symplectic structure, and the stratification is determined by the stabilizer group of the stabilizer group. Okay. So concretely speaking, we can write that SC as the disjoint union of SC alpha. This alpha is in some index set, and the theorem says that there's 2 points in the quotient space. They are located in the same strata if and only if their stabilizer group agrees up to a conjugation. It means that if the stabilizer group are conjugate to each other, then they are in the same stratum, and stratum is the boundary of another stratum if and only if its stabilizer group is conjugate to a subgroup of another stabilizer group, like this. So in fact, this stabilizer group, the type of stabilizer groups, the conjugacy class is equipped with a partial order. This partial order gives the boundary information of different strata. Okay. Okay. With this classic result, we have this one. The question: can we expect the superintegrability for the stratified symplectic space? It means that we consider this M to be stratified. This P must be stratified, and this B is also stratified. So how can we generalize the superintegrability? As before, the superintegrability is just from manifold to manifold to manifold. But for stratified space, we should give a good definition first. Here, this stratified Poisson and stratified trivial Poisson. So in fact, there's one big problem is that the arrows of psi and pi here it is quite complicated. It may be from one stratum to another stratum to this stratum. So it's quite complicated. So we cannot see that the dimension condition. How can we choose? Sorry, this one. Yeah. How can we choose the verify the dimension equation? So we should introduce a very good definition of this superintegrable system on stratified space. So we have this definition. This definition, we see that in general, this is some not technical, but we see that the main idea is the following. I will give you a picture in the next page. And you see that we want this psi and pi to be almost morphism. It means that although this is quite complicated for Okay, although it is quite complicated for these arrows, but almost all points in the stratum, almost all points are sent to one stratum. This is the key point. Although there are points are sent to here, are sent to here, or sent here, but I will see that almost all points. It means in another words, there's an open dense subset of this one. It will be sent to one single stratum and sent to one single stratum. This is our requirements. And also we need that the image, this image of this pan, it is also open dense here, open dense here. So with this, we can have this picture. This is the our definition. After this one, it means that we have an open dense subset for each stratum in the phase space. And if we restrict it, if we restrict this map to this open dense submanifold, then the arrows, the complex arrows disappear, and there's only one arrow for each from each domain of definition and the target. So for the third one, it means that okay, this is a manifold, this is a manifold, and this is a manifold. So we can say that we can use the Euro in the superintegrability in the Euro sense. Okay, now let's show. This is the picture, illustration of this one. For example, this is a stratified phase space, and this is stratified Poisson in the middle, and this is a base space. And maybe these arrows are quite complicated, goes here and there, but they're always an open dense subset, such that this goes to only one stratum, and this goes to one stratum. And the second part is also like this. They may go to in the same one, but it doesn't matter. And here, the third one, okay, goes here, and it goes here. Okay, just like this. So we simplify these arrows, and then we can introduce our Euro integrability as for manifolds. So now we have our main result. The main result is like this. Let's see GV, SLN, the special unitary group, and all the spin Calogero-Moser systems defined from the Hamiltonian reduction. It means the ordinary quotient. The ordinary quotient. And orbit is any orbit. And are super integrable. And with the torus dimension n-1, provided all the strata, it means that there's one condition that it means that for the XC, in XC, we need some point, at least one point X in the first one, it is regular. If this is not, this is the torus dimension is lower. It means the torus dimension, it varies, it changes if we do not have this one. We also have our superintegrability, but this one is just to see that we can fix the torus dimension in the maximum of torus. And we can have lower, for example, here, we see that this condition is necessary. This is an example. If we choose some C, A minus A, 0, 0, like this, we can see that this, the X and the gamma like this, they are in this form. And then the dimension of the strata is quite low. We know that for SU3 here, SU4 here, SU4, the torus usually is of rank 3. It's 4 minus 1, A equals to 3. And here, the phase space, the dimension is quite low. It's already 4. So we cannot see that it has a 2-dimensional, a 3-dimensional torus. So in this case, the stabilized group, there is something in U2 here. So, but we can see that we can see that in fact we know that, but not have didn't write it down. It is that if we do not require the torus dimension is n-1, we just see that it's a torus, then we can see that for all the we can get rid of this condition. But the torus dimension we should examine the in fact it is the type of B. It means the lower stratum of the B of the base space. For example, here this X, you see that this X, they have double eigenvalue here. It means that this irregular. This X is irregular. If this X is irregular, we may have some lower damping torus here. Okay. Okay, next part we will give you a very concrete example for SU3. The idea of proof is just following the Rashtikin's proof in 2003. We construct this S, this P, this B, and the key point is how to select the open dense subset. We should find a good open dense subset to guarantee that the errors there's no more errors, not so many errors. So we find someone, for example, we need gamma to be regular, and the diagonal elements are 0, some generic condition to guarantee that it is still open dense, and all these points are sent to one stratum. Okay. So let's see the SU3 case. For the SU3 case, we can see that we have some three. In fact, there are 4 types. First, Kc equals to 0. It is trivial. Kc is 0, and its all conjunct orbit is a point, 1 point, so it's trivial. The generic case, the generic conjunct orbit is like this. Kc is ABC, and ABC are distinct, and ABC is non-zero. So in this case, it is quite generically, it is a smooth. The phase space is a smooth manifold of dimension 6, and its corresponding stabilizer group is just the identity. With this U3 is the group of the unit of the root of unity, cubic root of unity. So, and the reason is we can select a good representation of this X gamma to show that first let X gamma to this paradise I lost. This first we diagonalize this gamma and write X to be like this, Xij. Then with this relation we can show that the diagonal part is of this 0, and the gamma is also regular, and Xij can be solved when I is not to j. And then we show that the two of the 3 elements of x1, 2, x1, 3, x2, 3 are non-zero. And then we get finally like this, we get the stabilizer group should be like this. It is a discrete group. And in fact, we can show that if we take this Z12, Z13, we can make it to be pure imaginary or real. So as you like, because there are still H inside, we can make like H X on this X. So we get this X, this Z, and we can solve this one. So finally, we can get x1, 1, x2, 2. They are free variables. They are action variables. Gamma 1, gamma 2, you can regard it as the angle variables. And rho 1, rho 2, here you can regard it. You can view it as the spin variables. So this is easy because the phase space is really a manifold. And there another case. It is like this: A equals to C equals to A0 minus A, because it is traceless. So in this case, the phase space is stratified with 2 strata. The maximum strata is of dimension 6 as before, and the corresponding stabilized group is also as before. Here we can see that we have this Z1, Z2, and the only for the maximum strata, the only thing is to for the phase space for the maximum strata in the phase space, we just let P approach to 0. Here, we just select this B approach to 0, and automatically C becomes 0. C becomes to -A, and everything is the same here. The interesting part, I would like to say that the interesting part is the lower stratum. The lower stratum, it means that the variables, the spin variables, rho 1 and rho 2 becomes to 0. They vanish here. So we get, in this case, the image of this the Poisson projection here, it is become a 2-dimensional space. So if we look at this sequence of arrows, we will get a real classic Liouville integrable. This line is superintegrable, and this line, the second line, is Liouville integrable. So, but we can see that in general, as a stratified space, we can say that it is superintegrable. Okay. In fact, for SUN, it is much more complicated. We can show that it has more stratification, more strata, and yeah, it has more stratum, and the idea is that we get rid of some points, and then we get rid of some bad points, and then the arrows becomes form a sequence quite clear. So, okay, I think it's here. Thank you very much.
Thank you very much. Questions?
Sorry?
The lowest stratum is of dimension 4.
Yes.
Okay, not 6.
Here, the lower dimension here is dimension 4. Here is dimension 6. This is a 6-dimensional strata, and this is a 4-dimensional stratum.
The second bullet is there, dimension 6, right? So it should be dimension 4, right? Second bullet.
Sorry, here. Sorry.
The lowest stratum is of dimension 4. In the bullet.
The second line. Second bullet. Sorry. Yeah, you are right. This is dimension 4. Thank you. This is dimension 4.
More questions?
Yeah. So the dimension 4, in fact, it means that these 2 variables disappear. In fact, in general, we have 6 variables as coordinates. And the last part, the spin variables, rho 1 and rho 2, they disappear.
Can I ask another question? So you said that in a SUN for higher n, it's more complicated, but do you always have a stratum which is Liouville integrable?
Not Liouville integrable. Always have superintegrable.
Yeah.
Yes.
But do you always have this bottom analog?
No. This is in fact, if n is much bigger, we have this one. The dimension decreases quite low, not quite fast. Like this is 6, 4. But in higher dimensional, it is the dimension of the phase space is always bigger than it's much bigger than the twice of this one. Twice of the center, the rank of the center.
Okay, more questions?
Yeah, because the rank of the center is always n-1 or maximum.
Would you please go back to your slides number 8? Yes, your mu sub ij, mu ji, j sub ji.
Yeah.
That is angular momentum. Is that correct, or just constant?
Yeah, no, that's not constant. They are the variables of the spin variables. It means there are some other ways to express this. This mu ij, you can consider that it is, if in the Euro sense, you can consider it's we introduce a vector. It is a vector and the inner product.
Related to pi qi or
No. It's new variable. It's independent.
Independent. Okay.
Right.
If independent, which means just view as constant, right?
For the Calogero-Moser, for the classical Calogero-Moser, it is constant.
I see. Okay. So question here: if you put qi minus qj square, what about n equal 3? Is that related to a three-body problem? If n equals 3, little n equals 3, that is related to the three-body problem, yes or no?
No, because three-body problem is just the you can see that the potential it is for Calogero-Moser it is a repel force. The bodies the force is repulsive, but for the three-body problem we all usually consider it is the contraction. It's attractive force.
Yeah, right. That's exactly the bottom. Its denominator must be
The denominator here.
Square. Yes, exactly. You can put the absolute values of square. Yeah, somehow there. That's my first question. Second question is go to page 9. Next page, actually. There you go.
Yeah.
So here you dimension manifold of M2N.
Yes.
So now you put k some numbers.
Yes.
So you have the submanifold, right?
Yes.
Which is M2 minus k, right?
Yes.
So if k equals even number, my question for you, that submanifold is still symplectic manifold, yes or no?
Sorry, you mean
my
if
question
k is even?
When k
is even.
So k could be even.
Yes.
Could be
Yes.
odd.
Right.
So you separate the k, right? If k is even, so your submanifold could because you notice here, your submanifold M2N minus k is could be symplectic manifold or not. So in general, it's a partial manifold.
No, usually it is coisotropic. You can consider it as coisotropic. It is symmetric plus some other Poisson bracket as they are the center inside.
Take this conversation.
Sure, no problem. We can discuss more details during coffee break.
We can answer your question in one phrase. It's like this. For this algebra, it has center. For if it is complete, it is symplectic. The Poisson center should be 0.
That a Casimir problem.
Yes, yeah, Casimir problem.
I'm gonna discuss with you later. Thank you. Sorry.
Thank you all very much for the questions. And let's thank the speaker again.